Hello students, welcome to Physics Wallah, GATE Wallah. I myself Shivam Dixit welcoming you all on behalf of GATE Wallah in this beautiful subject of thermodynamics. And we have already completed basic concepts of thermodynamics, first law of thermodynamics, second law of thermodynamics, entropy. Now if you see, there is one very small chapter, even it is just like a small topic that you might have already studied in during your 12th standard also, that is combustion and thermochemistry, right? Combustion and thermochemistry, it is a very easy topic, right? And a very small topic, right? Hard, like if you see, only one basic concept is there, that how a hydrocarbon is going to be burned, or how combustion is basically take place, right? Or combustion is nothing but what? Oxidation. So this, how this combustion or oxidation basically take place. But the good part is that maximum number of questions in aerospace is asked from this particular topic, even though it is a very small topic. See, if you look at like in last 5 to 10 years, if you see, like if you see the last 10-year scenario, I have seen that 7 to 8 questions are asked from this particular topic. Means almost every year one question is there, right? Almost every year or every 2 years there is one question from thermochemistry or combustion. And the good part is all the questions are exactly same, right? All the equations are only same, but you must know how combustion is exactly take place, how chemical reaction is going to be take place, and on the basis of that chemical reaction, what is the air fuel ratio, stoichiometric air fuel ratio, rich air fuel mixture, equivalent ratio, all these things are only going to be asked in different manner, nothing else. So it is a very small topic. Hardly conceptually, if you see, it is hardly, it will take 1 hour, that's it. So 1 hour hardly concepts will take, and 1 hour only questions are going to be take place, right? So it is very simple, very easy, and very scoring topic of thermodynamics. Because see, you have already seen their second law of thermodynamics or entropy, even first law of thermodynamics. So what I observed by seeing the previous year paper of aerospace engineering, that there are 2 3 topics from which frequently questions are coming. When it's about aerothermodynamics part, basic part of thermodynamics, if you see, then 2 3 topics are there from where frequently asked questions are there. The one is first law of thermodynamics. For closed system, open system, there are little less question, but it is there, right? So first law of thermodynamics is one of the very important topic as far as GATE Aerospace Engineering is concerned. Then the second most important, like if you see the second law in entropy, very less number of questions were asked, but whatever we discussed, that is more than enough to solve any problem, right? Any kind of problem, if it will be given, you can easily solve if you have revised entropy properly, second law properly. Then the next topic is coming like this, combustion and thermochemistry. That is very easy, very scoring, and many number of questions are asked. So we'll solve number of problem on this, and almost every type of problem we'll solve, which are already asked or which may ask in further upcoming exams. Then so 2 topics are very much important, right? First law of thermodynamics, thermochemistry and combustion, and third one is Brayton cycle. So let's start. So my audio video everything is fine. Very good evening and very warm welcome in this beautiful chapter of combustion and thermochemistry, right? Like what is combustion, if I ask you, right? See, I would like to share here. So basically today we are going to talk about the combustion. What is exactly combustion? What is thermochemistry? What is the fuel structure? How the fuel is going to be burned? And on the basis of that, how to write a stoichiometric air fuel ratio or stoichiometric equation of combustion? What is rich mixture? What is lean mixture? And what is equivalence ratio, and what type of questions are going to be asked? So these things we are going to discuss today, and these are the topics we have already discussed in previous classes. So I hope you have already completed all these things. And one very good point about this chapter, that it is not related to the previous chapters, correct? It is not, it does not have any relation with the previous topics. So this is completely independent topic, and most of you may have already studied this topic during their 12th standard or JEE preparation time. So you will feel that it's a very easy chapter for you, correct? It is going to be very easy chapter for you. So what is combustion? Whenever combustion words coming in front of us, so we feel that we are talking about something burning, right? Burning of the fuel. Burning of the fuel is basically combustion. And for us, fuel is nothing but a hydrocarbons, correct na? So fuel means, for us, if you talk about, fuel is nothing but what? Fuel means nothing but a hydrocarbon, right? Hydrocarbon. So hydrocarbon means hydrogen atom will be there, and uh, carbon atom will be there, correct? Like methane is there, and other than methane, we can say propane is there, correct? CH4, C2H8. So these are the basically hydrocarbons, and we are going to focus on these fuels only, right? Now the next point is coming, like, what is combustion? Basically combustion is nothing but what? Oxidation. Combustion is nothing but a oxidation. It is a kind of chemical reaction which is taking place in the presence of oxygen. It is nothing but a chemical reaction which is taking place in the presence of oxygen, or with the help of oxygen which is present in the air, because mostly we are not using oxygen only. Actually required is oxygen, but oxygen is not available free of cost. So in most of the cases we are using air basically, right? We are using air for our combustion purpose. Few of the engines are there, cryogenic engine if you talk about. So in that cases we have to send the air, because cryogenic engines are sometimes operating on the vacuum, where there is no air is present. In that case we always send the this oxygen cylinder only, so no need to send the air, right? Because that air contains nitrogen as and oxygen, and nitrogen is not going to help us, right? Nitrogen is even not participating in our chemical reaction, so that is basically unnecessary, like that is not required. But we don't have any other option, right? Normal situation if you talk about, we don't have any other option, because if we if we only use oxygen or oxygen cylinder for the combustion purpose, then it will be very costly. Actually it will be very costly. That's why we are using air for our combustion systems. And and in that air major portion is oxygen and nitrogen, and in oxidation, in combustion, only oxygen is going to be participate, nitrogen will be as it is, correct? Nitrogen will not take any part. Only thing is, whatever heat is going to be produced, a majority part of a large part of heat is going to be absorbed by the nitrogen. I'll tell you why. I'll tell you why. So basically combustion is the chemical reaction in which the fuel reacts rapidly with oxygen. Which oxygen? The oxygen which is present in the air, and releasing heat, and some combustion products also, right? Releasing heats and some combustion products. Mostly these combustion products are, I am telling you, mostly these combustion products are CO2, right? Mostly H2O, right? Like in every whenever any hydrocarbon is going to be burned, right? Or any hydrocarbon is going through a oxidation reaction, then CO2 will be formed, and even it is desirable also. At the same time, water will also form, correct? Sometime with the lack of oxygen, if oxygen is less or air present inside the combustion chamber is less, then CO can also be formed. So majorly these three things are going to be formed, right, as a combustion product, correct? If you are supplying excess amount of air, oh, nitrogen will be there obviously, right? Because nitrogen, because we are talking about here air, right? When we are talking about air, so in that air nitrogen is not going to take a part, so nitrogen will also be present. Okay, I'll write as a nitrogen also will maybe there, correct. Now, but mostly these three are called as our combustion products, correct. These three are, if we are using oxygen, if we are using oxygen only, then these three things are going to come, right. These three product will be there, and mostly desirable is only CO2 and H2O. What we want that after combustion whatever combustion product will release, in that heat will be there obviously, along with that heat CO2 is there, fine, H2O is there, fine. Sometimes CO is also produced, but it is not desirable because it is dangerous for the health. It is dangerous for the health. So CO is not desirable. Now, as I'm saying that we are using air, so in that air nitrogen will be present, correct. So that nitrogen will be as it is, come out as a combustion products also, and this is not harmful for us. Only the point is it takes lot of energy, and go into the surrounding. Okay, that is the only disadvantage. Otherwise nitrogen is not harmful for us, or not taking any reaction also. Now, as we are talking about here hydrocarbons only, so mostly only these things are going to be as a combustion products. But sometime in some of the fuel, some sulfur particle, let's say there, that is also dangerous, right. That is, so that sulfur particle may produce SO2, that may be possible, right. So that is also not desirable, and it is strictly banned nowadays. Pollution norms are very strict. You see nowadays Delhi condition, correct. Even most of the city condition is very dangerous nowadays. So government have very strict rules regarding this combustion phenomena, very strict rules. And SO2 is also very dangerous. So now we cannot use any fuel where sulfur is present, and the sulfur is going to be in oxidation reaction and going to produce SO2, so that is not desirable for us, correct. So this is basically combustion. So what is basically happening in this combustion phenomena? Question is coming like, combustion, what is this actually taking place, what is happening in this combustion phenomena? So basically we have fuel, right. Fuel means hydrocarbon, we can say CXHY, right, like CH4, right, C2H H6, right, so C8 H10, right. So you can see that this is a hydrocarbon. Fuel is basically hydrocarbon for us, right. So hydrocarbons are there. Then here oxygen will come, right, oxygen will come into the picture. Then reaction is going to be played, and now this is desirable is what, oxygen only, right. But along with oxygen nitrogen will come free of cost, but for time being we are only considering oxygen. Later on we'll consider nitrogen also, so just wait. Just I'm telling you what is ideally a combustion reaction is. Now then after this oxidation or combustion, here oxidation will take place, or combustion will take place, and it will form the heat, and then plus combustion products. So in our case combustion products is nothing but mostly it is CO2, H2O, and sometimes CO, and even sometimes carbon particles also there, right. If you go and check, mostly in your bike it will not be there, because nowadays carbon particles are also very dangerous. If it is very fine particles are there roaming here and there in air, and when you are inhaling this, it is very dangerous. So nowadays it is not there. But if you see older days, if you remember, most of the vehicles, if you see, in that exhaust of that vehicle, right, if you touch that, then carbon particles are there. So like carbon particles are also there, right, carbon particles, sometimes carbon particles are also present, right. it is okay, it is desirable. These are not desirable, not desirable. This is not desirable, this is desirable. Desirable. Sir, but CO2 is also harmful, na? Yeah, CO2 is also harmful, but if you are saying that the CO2 will also not form, then where this carbon will go? Correct, na? So obviously, CO2 is not that much harmful, I'm telling you. CO2 is not that much harmful if it is coming in a limited condition, because we have trees, right? So that trees, what they will do? That trees will convert the CO2 into oxygen again, right? So there is no much problem with the CO2. So actually we want in the combustion products only CO2 will be present, right? And H2O should be present. CO2 should be present, H2O should be present, CO and C particle should not be there. But sometime due to uh, uh, lack of the air in the combustion chamber, lack of the oxygen in the combustion chamber, or due to not a proper combustion is not taking place in some cases, this is also there, right? This is also there. And that is the reason that very strict pollution norms are formed. Even you have seen that now you have to check your vehicle every 6 months, right? And you have to generate one pollution certificate that your vehicle is okay. Because if your vehicle is producing CO or C, then you cannot run that in a road, right? Government will not allow you. Ideally they will not allow you, but sometimes people are using, people are 20-year. I have seen that 20-year Chetak also people are running. Old Omni 800 is also running in the in road. They are not actually satisfying the pollution criteria, but still, this is India, right? If you have some money in your pocket, then you can run anything, right? But standard, like ideally, if you see, very strict rules are there, and you may have to give a large fine, 20, even up to 25,000 fine is there, right? But if suppose one policeman is asking you 25,000 challan will be there, you know how to save your 25,000 by giving some 2,000 rupees, correct? So that things are different, but actually it should be like this. So this is basically our ideal combustion phenomena. Now let's talk about another thing, that is what is this thermochemistry, because this chapter name is combustion. Hopefully you understand. Combustion is nothing but what? Combustion is burning of the fuel means hydrocarbons, for our case, right? Hydrocarbon. Then another word is oxidation. Combustion is also another word is oxidation. Another word is it is a chemical reaction. It is a chemical reaction which rapidly taking place with the oxygen. Combustion, like these hydrocarbons are going to be rapidly oxidized with the help of oxygen present in air and form heat and combustion products, correct? So what are the possible combustion products? That also I have told you. Even SO2 may also possible, but nowadays it is not there. In our course especially it is not there. And then what are the possible combustion products? What are desirable combustion products? What is the non-desirable combustion products? All those things we have already discussed. Now come to the another one, that what is thermochemistry? Thermo means what? Thermo means heat. We have already seen, right? Therm means heat. Therm is a Greek word that means heat, and that heat is mostly coming from where, right? We are mostly in our engines and every places we are transforming this heat in like from the fuel. We are burning the fuel. If you look at the any engine, then what is happening in heat engine I'm talking about, then we are supplying fuel, we are supplying air, then air and fuel is going to be oxidized, air and fuel mixture is going to be burned, then heat will produced, right? Heat will produce, then this heat will transfer, and then it will further transform into the work. There are two words you have seen, right? One is transfer of energy, another one is transformation of energy. Means if energy is if energy is moving from one place to another place without changing its form, let's say some heat is here and it is moving to here, that is called as transfer of energy, correct? Like here some work is there, that work is moving here, there is transfer of energy. Some electrical energy is there moving here, that is transfer of energy, right? But if one form of energy is converting in another form, that is called as transformation. For example, you have electrical energy, now it is going to a bulb, and that bulb is converting this, transforming this energy into the heat energy or light energy, correct? So that is transformation of energy. So here also in combustion also, basically it is a transformation of energy. Chemistry is also involved, obviously, because chemical reaction is take place. As a chemical reaction is going to be take place, so chemistry is also required. So basically therm means heat. That heat is going to be produced or transformed with the help of combustion of the fuel. As the fuel combustion is going to take place, that is nothing but a chemical reaction is involved. Chemical reaction is involved means chemistry is involved. That's why this branch of science is named as a thermochemistry. This branch of science is called as a thermochemistry, where a fuel is going to undergone a chemical reaction and producing heat or transforming into heat. Now the question is coming like, okay sir, I understand this, but here what is happening? Transfer of energy is happening or transformation of energy? Obviously transformation of energy is happening. What kind of energy is transforming to other form of energy? So basically what we have here, we have chemical energy, right? Here we have chemical energy, green, chemical energy is green, that's a chemical energy of fuel, that is nothing but CXHY, right? Chemical energy of the fuel, right? Now this chemical energy of the fuel means hydrocarbons are going to be undergone an oxidation reaction, right? Or oxidation in presence of oxygen, right? That is also, this phenomena is also called as combustion and producing heat, same thing, heat. So basically chemical energy is going to produce into the heat. Obviously some combustion products will be there, that is a side product, we don't require it. This combustion product we don't require any combustion product, but it is a byproduct, right? So we will release into the atmosphere, simply we require only heat. So heat we will utilize combustion product. Sir, what do you mean by this chemical energy of the fuel? What do you mean by chemical energy? Let's say you have let's say C2H6, right? For example, you have C2H6, so C, and here we have H, 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 here we have H. So basically this C2H6. Now if you look at this C2H6, then they have bonds between carbon, right? Carbon and hydrogen, you can see carbon and hydrogen have a bond, right? Here you can see that these bonds are there, right? These bonds are there, right? So when this oxidation is going to be take place, when this oxidation is going to be take place, then these bonds are going to be break. These bonds are going to be break, basically these bonds are going to be break, and when they will break and make some other kind of bonds with oxygen, they will make some other kind of bond, right? And then lot of heat is going to be produced. That is basically the energy stored in the bonds. You are getting my point or not, right? So that energy itself is called as a chemical energy, and that is going to produce that is going to convert into the heat. I will give you one simple example, then hopefully you will understand that what is exactly happening, right? What is exactly happening in this particular thing, right? So first I will take the example of CH4, right? So CH4 means we have one carbon atom, and that is making bond with hydrogen atom, 4 hydrogen atoms, something like this, right? Then we have oxygen, plus we have oxygen O2, right? O2 there, O2 is there, right? Now what will happen actually, please try to understand what will happen. We have to see, here fuel is there. For example, here I have methane. Oxygen is already there in the atmosphere. Is it start burning automatically? No, you have to start the combustion phenomena. You have to start the combustion phenomena by spark or by lighter or by matchstick, right? So you have to start, you have to give some initial amount of heat first initial. So when you give some initial amount of heat, then what is going to be happen, please try to understand, right? What is going to be happen? These bonds are going to be break, right? Let's say one molecule of CH4, first molecule of CH4, what is going to happen? That bonds are going to be break. When bonds are going to be break, then what you will have? We have one hydrogen here, we have one another hydrogen, another, or 4 hydrogens are breaked, and one carbon dioxide also. I'll draw right here, carbon dioxide also, correct? Okay, fine. Now hydrogen, right, at the if you have already studied in your during 12th standard, that here at outer cell we have only one atom here, one atom is there, right? So it can make only one bond. So what will happen? And obviously this oxygen is also there, that will also break, means we have oxygen particles also. This is oxygen particles, right? We have oxygen particles present, right? So what is going to be happen, please start to understand that one oxygen atom will come here, one oxygen atom will come here, right? One oxygen atom will come here. Now at outer cell, if you see, at outer orbit, if you see, in oxygen how many atoms are there, right? 2 atoms are there, right? Let's say here 2 atoms are there. So basically it can make like it can, and here how many atoms are there? Here one atom is there, here one atom is there, here one atom is there. Now so actually now bonds are going to break, but it's again hydrogen, only hydrogen is not a stable state, right? Suppose when these bonds are break and hydrogen come out, right? But this hydrogen outer cell have only one atom, so that is not a stable state, right? So it actually it wants again to make some bond with someone, right? It again wants to bond. Actually you think like this, earlier these carbon have 4 girlfriends, for example, and just take a light note, right? So if this carbon have 4 girlfriends, for example, initially, and they have very good bond and they are in stable position, but someone came, put fire, say something, or yeah, he is not a good person, right? I have seen one person, that name is Oxygen, he is a very handsome, correct? So he have 4 girlfriends, right? So why you are wasting your time? Separate. Okay, so what is happening by listening all these things means matchbox, right? So what is happening, these hydrogens are separate, but now hydrogen is single. Now hydrogen, all these hydrogen girls are singles, right? So they are ready to mingle, obviously, because that is not stable state. How they will do the shopping? How they will do the shopping? So they also want someone, right? So what is happened? And this oxygen is also separate here. Oxygen outer cell also have two, right? Two atoms. So they also wants to make a bond for stable equilibrium. So what is going to happen, one particular oxygen is going to be make a bond with one hydrogen, one bond is formed. This is in stable state. Now this is like she is on stable state, hydrogen is in stable state, but oxygen is still not stable state. Oxygen is not good type of person, correct na? He's a kind of these core branch na aerospace type of person, right? He's a aerospace type of person, so he required not one, minimum two should be there, one option should be there always, right? So what he did, he make one another bond with another hydrogen, right? So basically what is formed, basically what is formed from here, here it is they formed H2O, they formed H2O. What, wow, what a stable state, what a beautiful state, I would say. Similarly one more oxygen will come, one more oxygen will come here, which have again two atoms at outer shell, and then they here also they are going to make a bond. Here also they are going to be make a bond, and they will make one more H2. Two hydrogen, like 2H2O is done. 2H2O is done. Fine, perfect, perfect. Now who is remaining? When this bond is breaked, then who is remaining now? Sir, I think carbon is remaining, sir. Carbon is remaining. That is the problem, right? Carbon is still remaining. Oh, carbon. What to do with carbon? Yeah, carbon is very dangerous. Carbon, I will draw with some this color. This color, yellow color. Okay, yellow name, pink color only, purple color. So here we have carbon. Now carbon have what? Carbon capacity is very high. It is a mechanical type of person, right? So carbon have four at outer shell, four atoms are there. So he want again four. Earlier he have four, right? Again he want four. So what he will do, right? What he will do? But she is not ready. She is not ready. So obviously what he will do? He will call one person, right? One person like oxygen, right? He will call one person, that is oxygen. So one oxygen will come here. One oxygen will come here. One oxygen will come here, and oxygen outermost have two atoms. So these two bonds are going to be formed, right? These two are going to be formed like this. This is going to be bond. Correct. Similarly, one more oxygen is required. Here, one more oxygen is required. That again have two. Then again, it will make one more bond. It will make one more bond like this. So now, from here, we'll get CO2. CO2. Now, this is also perfect stable state. Perfect stable state, right? Okay, so now see here what happened basically. So we have CH4 plus oxygen was there, oxygen is available, right? Then oxidation is going to be take place, or combustion is going to be take place, right? Then after combustion, what is going to be formed? 2H2O is going to be formed, right? 2H2O is going to be formed. Very good, fine. 2H2O is going to be formed, and one CO2 is going to be formed. One CO2 is going to be formed. Okay, now question is coming like, how many oxygen atoms are required? So this is one O2 required, two O2 required, and three O2 required. So total 3 O2 is required. Now this is a perfect chemical reaction you form. Plus heat will be there, obviously. Plus heat will be there. Right? So this is a perfect chemical reaction, or later on you will understand this is a stoichiometric reaction basically, correct? Now what is stoichiometric reaction? Just wait. So I hope you are able to understand that how this uh, uh, thermochemistry or combustion reaction is going to be take place. But now I will tell you one much better way, actual way, that how the fuel structure is there, how the, like for hydrocarbon, how the fuel structure is there, how it is going to be burned, right? And like how you have to balance the equation, and how you have to think that how the chemical reaction are going to be formed. For that purpose, actually, you need to understand. For that purpose, you need to understand what is the fuel, like what is the fuel structure. Achha, one more thing I would like to share here. Before fuel structure, I would like to tell you about air, because air is also going to be participate here. Generally, the air which is available in the atmosphere, that is called as moist air. I don't know whether you know or not. That is called as moist air. Sir, what is this moist air? Actually, this moist air have two things, right? Majority it is a dry air, and a little bit of water vapor is there. Water vapor is there. Water vapor is also present. That is called a humidity. Basically, in north side, if you see Delhi, UP, and all, and the humidity part, water vapor part was less in rainy season. It is little bit more, but overall it is less. But sea regions like Mumbai, if you see Chennai, if you see, right, so in these places, Kolkata, if you see, so these places basically it is more, right? It is more, right? Okay, no problem. So water vapor. But when we are going to analyze here, which air I'm not talking about the moist air. Whenever we are going to write the equation, we are not talking about the, even though it is a very stable state, water is a very stable state, that is also not going to take part in the combustion. So that will also go out simply, and we are not considering. So this we are not considering. This part we are not considering. So basically we are talking about dry air. Now what do you mean by dry air here? So further, if I classify here, so in dry air we have three things basically, right? One is the oxygen, we have O2 majorly, nitrogen we have, and some traces of like CO2 is there, maybe CO is there, maybe SO2 is there, maybe some other traces. These are traces, even less than 1%, right? Even less than 1%. So these things also we are not considering in our analysis. This is also not considered in our analysis. This is also we are not considering. So basically, when I'm saying that air, what do you mean by it? It does not mean the actual air present in your room, right? Actually, it is moist air, in which a little bit part of water vapor is there, little bit part of CO2, CO, or other gases may be there, may not be there. Correct? It depends actually location wise and all, right? In Delhi, if you see, maybe CO is also available, but I'm in Lucknow, so mostly carbon dioxide is only there, right? So okay, in Delhi maybe carbon particles are there, AQI dust particle may be there, correct? So those things we are not considering in our analysis. So when I am saying that air, it simply means that oxygen and nitrogen. Generally, in this one, if you see that 17, only these two I am talking about. So generally what is happening that 21% oxygen is there, and 79% nitrogen is there. Volume basis, this is a volume basis. This is basically what volume basis or molar basis. Volume basis, or also called as molar basis, same thing, molar basis. If you have heard Avogadro hypothesis, then you know that volume basis or molar basis both are same thing basically. Okay, so volume basis or, and that is only required for us. So what it means actually, it simply means that if you have 100 mole of, for I'm telling you, if you have 100 moles of air, for example, right, air particle. If you have 100 moles of air particles, which the air which I am talking about, in that one 21 moles of O2 will be there, right, and 79 moles of N2 will be there. Means for every one O2 mole, what it means that It simply means that for 1 mole of O2, right? If any, like with 1 mole of O2, how many moles of N2 are present? 79 by 21, 3 point something it will come. 79.79 by 21 moles of N2 is going to be present. N2 is going to be present. Is it clear? Right? Is it clear? Correct. So basically, you can see that in our case, you assume that it is in packets basically, right? Let's say you are using 1 mole of oxygen, right? If you are using 1 mole of oxygen, right? So if you are using 1 mole of oxygen, 1 mole of, if you are using 1 mole of oxygen, then by default, actually we require what? Let's say in some chemical reaction you require 1 mole of oxygen, but by default with 1 mole of oxygen, 79 by 21 mole of N2 you will get free, completely free, completely free. Correct. And I have already told you that mass is equal to what? N into capital N, right? This also may be required, right? Mass is equal to number of moles into molecular weight, right? Means with, if I convert this in mass also na, then also we can write like what is the mass of 1 mole of, right? Means 1 mole of O2 and then 79 by 21 mole of N2. So here how much mass will be there? Mass is equal to number of moles into molecular weight. So this value will come 32, right? Molecular weight is 32 here, and here it will come 79 by 21 times of 28. Correct? So let me calculate this. I have a calculator with me. Where is my calculator? Gone? Arey, who is taking my calculator? Yeah, okay. So this value will come 79 by 21 into 28. Correct? So it will be how much? Sorry, 79 by 20, 21 into 28. So here you will get equal to 105.33 mole. So total, how much it will come? Total air will come, like if you combine this one, then you will get 1 mole of, like, so total it will come air. This is the mass basically, plus 32 if you do, you will get a 170, oh sorry, 137.33 mole of air. Now if you calculate percentage now again O2, so 32 divided by answer, so you will get a 23%, 23.3% oxygen you will get, right? And nitrogen, how much you will get? Nitrogen you will get a 105.33 divided by 137.377 something it will come, right? Okay, approximately 76.7%. So what I'm trying to say, what is our conclusion from here? The conclusion is molar basis. If you see molar basis, volume basis, right? If you talk about molar basis or volume basis, 21% oxygen we are considering, 79% nitrogen we are considering. But if you take mass basis, then 23 approximately we are taking 23% oxygen we are taking, or 77% nitrogen we are taking. So mass basis, if you talk about, right, if you talk about mass basis, this will be 23% mass basis. This is just the structure of like air I'm talking about. In air, what is the proportion? Because this proportion is required for us in future, and this will be 77% N2 O2 mass base. Sir, why volume basis night oxygen is less and mass basis is more? Because the number of moles are okay, but 1 mole weight is more, right? The molecular weight of oxygen is more, 32, and 2 is 28. That's why when you talk about mass, then even though number of moles are 21 only, but mass will be one mole of 1 mole of oxygen is heavier basically, right? 1 mole of oxygen is heavier compared to nitrogen. That's why mass basis percentage is little bit different, correct? So I hope this part is clear to you. First everyone write this. Everyone write this one. Please everyone write this. So I hope you are able to understand what is combustion, what is thermochemistry, and what is the air compositions, right? Air compositions, I hope you are able to understand. I hope you are able to understand. Okay, shall I move? Okay, let's move to the next part, that is fuel structure. Now you need to understand the fuel structure of any hydrocarbon. So basically in hydrocarbon, what we have, carbon atoms are there and hydrogen atoms are there. Now carbon is 12, carbon molecular weight is 12, hydrogen is 1, right? It means that hydrogen is lighter. Please listen here carefully. Hydrogen is lighter as compared to carbon. Is it clear? Is it done? Ankit, you tell me, right? So if you are going to compare, like suppose you have a hydrocarbon, so in that hydrogen atom will be there obviously, and carbon atoms will be there. But if you talk about the molecular weight, weight wise, if you see, carbon is 12, correct? Carbon molecular weight is 12, hydrogen is 1. So hydrogen is lighter, so that's why it will be always on the surface, right? Suppose if I represent, suppose this is a some, it is some, like let's say fuel particle I'm talking about, one, let's say CH4, let's say it is a CH4 molecule, for example, CH4 molecule. In that, what is going to happen at the core? Please try to understand, at the core, at the center, carbon will be there, because carbon is heavier, and oxygen, hydrogen will be surrounded by it. It is outer, it is like floating, right? It is something like that, right? So here we have, this is called as core, and at core basically carbon is there. At core, what is there? Carbon is there. Please try to understand, carbon is there. So at core, carbon atoms are there, correct na? At outer surface, hydrogen is there. At outer surface, hydrogen is there. Is it clear? Correct. Please start one, because hydrogen is lighter. Here I can say that hydrogen is, H2 is lighter than carbon, or H2, no, I write H. Hydrogen atom is lighter than carbon, because is carbon is, or I can say carbon is 12 times times more heavier than hydrogen. More heavier than hydrogen. Now whenever you are going to spark or ignite, whenever you are going to spark or ignite or matchbox, you are, suppose this is one molecule of some CH4, right, something, right, hydrogen, this also I write H only for these H items, right, H item, something like that. Not H2, I will write here H, right. So at the core we have carbon, at the outer we have hydrogen. Whenever you are going to burn, please listen here carefully, whenever you are going to burn with the help of matchbox, lighter or spark plug, right, so whenever you are going to give here spark, right, let's say you are going to give the spark, whenever you are going to give spark, right, this is basically what, a spark. Whenever you are going to spark, then what will happen, few rules it is going to follow, that you need to understand very carefully, because once you understand the rule that how this combustion phenomena is going to be take place, this chapter will be in your fingers, I'm telling you, right. The first very important point, that first hydrogen atom is going to burn, are going to be separate or going to make a bond light, right. So in simple layman language, if I say, first hydrogen is going to be burned, first hydrogen, it is actually step by step, hydrogen is going to burn, first hydrogen is going to be burned, and this is very rapid, burn rapidly, or I can say fast. These each and every word is here very much important, each and every word is very important here, that whenever you are going to give a spark to any hydrocarbon, then first hydrogen will burn, right, layman language, hydrogen will burn or hydrogen will oxidize and make H2O, like that. This is a scientific language. Scientific language, what is there, that first hydrogen is going to be oxidized and going to make H2O, right. Or in layman language, I can say that first hydrogen is going to burn, but the very important point here, that this burning is going to be super duper fast, super duper fast, super duper fast. It is going to be within a fraction of second, the hydrogen atoms are going to be burned, right, hydrogen atoms are going to be burned. Then carbon burn after hydrogen and little bit slow compare to hydrogen, because it burn in stages. Each and every word is very important here. See here, outer surface, what is there, hydrogen, when they got spark, within a fraction of second, within a fraction, zoom, right. So initially when you burn, you have seen that blue light is coming, blue flame is formed. Blue flame is because of hydrogen combustion, and after that red flame will come. Red flame is because of carbon combustion. Now please listen here carefully, that carbon is burned after, sir, but why it is little bit slow? That is also very fast. In our scenario, if you see, it is in fraction of second, but compared to hydrogen, it is slow actually. Why? Because it is taking place in a in stages. Sir, what do you mean by stages? Stages means basically, first what is going to happen, let's say you have carbon, right? You have carbon, then this carbon will oxidize in presence of O2. First stage it will form CO. Please listen here carefully. First, whatever carbons are there, that carbon will form CO. Then CO will further react. CO will further react with oxygen and form CO2. What is our desired? Arey, listen, Babu. What is our desired? Desired is CO2. But CO2 will not form directly. This is very much important. First, all the carbon atom will form CO. First, all the carbon atom will form CO. And once they will form CO, then further they will oxidize and form CO2. So this is the first stage. This is the first stage of combustion, carbon combustion. This is second stage. That's why it is taking little bit time. That's why it is taking little bit time. I hope you are able to understand, right? And even if you want, you can write one point also. Which color should I use? This color. Blue flame is because of hydrogen combustion and after that red flame is because of red flame is because of after that red flame is because of carbon combustion. I hope this is very much clear to you all, that what is basically the fuel structure, right? What is basically the fuel structure? You might understand this, and how this reaction is going to be take place, right? How this reaction is going to be take place, or how the one particle, one molecule of the hydrocarbon is going to be burned. So please listen here step by step. Whenever we are going to give spark to any hydrocarbon, first what will happen? First, all hydrogen will burn immediately and form H2O. Correct? All hydrogen will form H2O immediately. Then what will happen? Then all carbon will convert into CO. Once all carbon will convert into CO, then further they will react with the third stage. Further CO will convert into the CO2 with the help of oxygen. Let's say all the carbon converted into CO, but after that O2 is finished. O2 is not there, right? Oxygen is finished in the cylinder. Oxygen is finished in the combustion chamber. Then what will happen? CO will be remains. And it will come out as a combustion product, and it is very, very dangerous. Then government will shoot you. Why you are producing CO? Correct? Then you have to give the fine. Correct? So if you want to save, fine. If you want to save your money, then you have to supply enough amount of oxygen so that this CO will also convert into CO2. If CO2 is forming, no problem. That's why you might have seen that CO is mostly colorless gas. Correct? H2O is also at very high temperature, right? H2O is steam, right? Steam form, it is not liquid form. H2O, don't think that it is a whatever H2O will form, that will be liquid state or water droplet will come. No, not water droplet will not come. It is at very high temperature, 2000, 1500, 2000 degree temperature. So it is a basically very high temperature steam. That is a high temperature steam is also colorless, correct? So you will not see, nowadays you can see that if you look at the silencer of any bike or any car, there is no smoke. Smoke is there, but that is not visible to you. Why? Because in that smoke only two things are there: H2O, that is also a very high temperature, right? And CO2, and CO2 is also transparent. Steam at high temperature is also transparent, so you will actually not see anything. But if your engine is not maintained properly, then what will happen? Then CO formation may be there and CO is visible, right? CO is visible, right? Gray color smoke will come. And if black color dots are also there, black color carbon particles are going to be, means it is very, very dangerous. You have to scrap your car immediately. Whatever vehicle you have, scrap it. I will suggest you, because nowadays pollution is very, very dangerous thing. One report I was I was seeing that in Delhi the situation is like, even the person who is not smoking cigarette, because of the air pollution, they are smoking approximately 20-25 cigarettes every single day. That much carbon they are inhaling. Very much dangerous, right? Very much dangerous. Okay. So I hope you all able to understand what about the fuel structure. Anyone have any doubt, you can ask. Up to here, if anyone have any doubt, you can ask. Then I will give you some examples also. Some note points I would like to give you here first. Have you written this? Have you written this? Have you written this? Okay. So some note points I would like to give here. The first is, in the process of combustion, hydrogen will first react with oxygen. This is the first point I would like to give. Correct. This is the first point I would like to give, that you need to write. Carbon dioxide start after hydrogen, right? Carbon dioxide will react after hydrogen. Once hydrogen, all the hydrogen will be over, then only it is going to be react. Then hydrogen combustion will be very, very fast. Hydrogen combustion is going to be very, very fast. I have already told you that, within a fraction of second. Carbon combustion will take time, because it will complete in stages. It is going to complete in a stages. Fine. Blue flame is because of hydrogen, after then red flame is coming because of the carbon. That is also we have done. And okay, then when you burn hydrogen, please listen here carefully. When you burn hydrogen, it primarily form the water. It primarily form the water, because whatever hydrogen atoms are there, that is going to, I just have seen that, I have just few slide back I have shown that hydrogen is going to combined with the oxygen and going to form the water. It primarily form the water and release significant amount of energy, correct? When hydrogen atom is going to be combined with the oxygen atom, significant amount of heat is going to be produced. Even I forget to tell you the amount of heat produced. Please listen here again. The amount of heat produced due to combustion of hydrogen atom is much greater than carbon atom, right? This is very much important part, right? This is very much most of the time people are saying that how you are getting energy? Carbon, we are burning carbon and we are getting energy. No, baba, right? In hydrocarbon means we are not burning coal here. If you are burning coal, then it is a different scenario. But whenever you are burning fuel, liquid fuels I'm talking about, or hydrocarbons, then the energy released due to hydrogen is much greater than the energy released due to carbon particles, correct? Carbon atoms, right? So when you burn hydrogen, it primarily form water and release significant amount of energy per unit mole. In contrast, carbon combustion produces carbon dioxide. Final, I'm talking about carbon dioxide releases less energy per mole compared to hydrogen. That's why hydrogen combustion is more energy dense. That's why we always call it hydrogen is a good fuel, very good fuel, very good fuel. Why? Because it is a high dense energy. High dense energy is there with the hydrogen, right? So future fuel is hydrogen only. Future fuel is hydrogen. Future is hydrogen, right? Because sir, no. Future is EV, electrical vehicles. No, but electrical energy is coming from carbon, bhai. Electrical energy, right? EV is fine, right? EV you can use, but from where you are getting electricity? NTPC. NTPC is burning what? Coal. So basically, it is indirect way. Earlier we used to put our pick our ear like this. Now we are picking like this. That is the only difference, nothing else. Okay, efficiency wise it is good. So this is EV is not it is temporary solution of energy. No. It is sorry. EV is not a permanent solution of energy. It is temporary solution or making it more efficient. That's it. And pollution is going to be decreased. That's it. Okay. Now the another very important factor that what about solar energy, wind energy, renewable energy? Renewable energy is also future, but I personally feel that renewable energy cannot alone fulfill the requirement of the energy, right? The amount of energy nowadays we required, because our like the living standard of human is increased like anything, correct? So the in this high-tech living standard, the amount of energy that is required to us, renewable energy cannot satisfy this. So that is good. Renewable energy is very good, but it is actually degraded form of energy. Sun is sending a lot of energy, but that is degraded form of energy. To collect that energy and convert into useful amount of energy, that is very, very difficult, right? That is not that much efficient, in simple words, right? So that is a problem. Storage is a problem. Storage is also another big problem. So I personally feel that the future fuel is going to be hydrogen, right? Future fuel is going to be hydrogen, right? Okay, but how, that I don't know. And you people have to do the research on this. Okay, so that's why hydrogen, right? Hydrogen, okay, high density, right? Okay, up to now you just write only these 3 points are something different. I did not explain yet. So these 3 points I did not explain yet. So first you just write these 6 points. First you just write these 6 points. Then I will go to the next topic, right? Like next slide. Okay, Aditya Narayan, in which one produce more heat? I told you, Aditya Narayan, hydrogen produces more. Sir, hydrogen has less molecular mass but have more energy per than carbon. Yes, Aditya Narayan, correct. That's what I written here. That's what it is written here. Don't worry. Sir, please note it down. Please make the notes properly, right? Now whatever we understand, a few things are still there. Whatever we learn up to now, that we are going to uh, see with the help of one example, and with that example I will let you know 3 more things, that is stoichiometric air fuel ratio or fuel air ratio, rich mixture, lean mixture, and equivalence ratio. These 3 things still will learn. So that's what I'm suggesting you. Don't write these 3 parts, only you write these 6 parts. Done. Shall I move forward? I will again come back to this particular. Okay, have you written this? Okay. Okay, go back to the thing. Now I am going to take the example of some example I'm going to take. Which example should I take? Okay, simplest fuel I'm taking methane, right? CH4. So I'm writing here combustion of CH4. Combustion of CH4. Combustion of CH4. Right? Okay. Complete combustion only we'll talk about. So let's start. So what we have, basically we have CH4. Then what we have, let's talk about first only and only, let's say we have oxygen only, direct oxygen we have. Later on we'll introduce air also. First assume that we have oxygen here, oxygen O2, direct O2 is there, only O2 is pure O2 is there, oxygen cylinder we are using for example. Okay, then what will happen step by step, then here oxidation is going to be take place or combustion is going to be take place. Combustion is going to be take place, oxidation is going to be take place or combustion is going to be take place. Now what will happen step by step, what I told you, this is a one part, like 1 mole of, for example, or 1 particle of a CH4 for example. Then what will happen, carbon will be at the core. Yes sir. At the outer part what we have, at outer part what we have, 4 hydrogen atoms. When you start combustion by spark or something, then what will happen, first these hydrogen atoms, right, will burn rapidly and form H2O and heat. So what is going to happen, with all 4 hydrogen atoms are going to form H2O, directly writing H2O, no problem. H2O. So here how many hydrogen atoms are there? 4 hydrogen atoms are there. So how many H2O items they will form? 2 H2O items they are going to form. 2 H2O items, because total 4 are there, right? So total 4 are there. So these 4 are going to form 2 hydrogen, right? 2 H2O, basically 2 H2O is going to be formed. 2 H2O is done. Yes, done. Now what is remaining in the fuel? Now carbon is going to be remaining. So what will happen? First carbon will convert into CO, but we are talking about complete combustion. Complete combustion means what? Complete combustion means in the final product, CO2 should be there, no CO is there. See, if CO is there, then incomplete combustion. If CO is present, then it is incomplete combustion. So basically this CO is going to form CO2. How many carbon atoms are there? Only 1. That's why only 1 CO2 will be formed. Correct? Now how much oxygen is going to be required? So you can see that 2 oxygen atoms here, 2 here, total 4. Total 4 are required. Here 2 is already there, 2 O2. Now if you see, the equation is completely balanced. This side how many carbon atoms are there? 4. Here how many are there? 4. Here how many carbon atoms are there? 1. Here also 1. Here how many oxygen atoms are there? 4. Here also 4. Correct now? It is perfectly balanced. Plus heat will be there, obviously. Plus heat will be there. Right? This is a perfect combustion. This is a perfect combustion, right? Perfect combustion. Okay, now do one thing. I will write, this is the case when oxygen cylinder we are using. But actually, are you going to use oxygen cylinder? No, you are not going to use oxygen cylinder. What you are going to use? You are going to use air. When you use air, my dear student friends, then what will happen? Then here CH4 will be there, obviously, right? 2 O2 is required, basically 2 O2 is required, but right, but with 1 O2, please listen here carefully, with 1 O2, 79 by 21 times of nitrogen is free. So if you require 2 O2, then how much nitrogen is required? 2 into 79 by 21 N2. free, Babu, free. So this is going to be free. Then combustion is going to be take place, right? Now here 2H2O will be there obviously, plus CO2 will be there obviously, plus. Now whatever nitrogen is there in left hand side, same nitrogen is not going to participate in the chemical reaction. You can write also. You can write as a note I given na. One more note you write, nitrogen is not going to participate. Nitrogen is not going to participate in combustion equation. Nitrogen is not going to participate in combustion equation. Correct? It is not going to participate in a combustion equation. So as it is, it will come out. Means it will come out like I'm not calculating, 2 into 79 by 21 times of 2 plus heat. Achha, the nitrogen does not have any role. No, one role is there. It will waste some energy. It will carry some energy. Sir, I did not understand. Okay, for example, whatever air we are using here, what is the temperature of that air? What is the temperature of that air? Mostly 30 degrees centigrade air or 40 degrees centigrade. So here assume that 30 degrees centigrade air is going to be used, right? Now after combustion temperature will increase, right? So okay sir, but this nitrogen temperature will also increase na. So initially same amount of nitrogen is there with low temperature. Now same amount of nitrogen is there with high temperature, and that is going to the surrounding. So nitrogen is carrying a big part of, right, a large part of energy to the atmosphere. That is the disadvantage of nitrogen. If nitrogen is not there na, so the useful energy which is produced will be more, correct? So this is one disadvantage, but we can't do anything. Okay, now come to here the point. This is a perfect combustion, right? This is called as what? Perfect combustion. This is called as a perfect combustion. Perfect combustion. Or stoichiometric reaction. Stoichiometric reaction. Sir, what do you mean by this perfect combustion or stoichiometric reaction, right? Stoichiometric reaction or perfect combustion, the meaning I will like to tell you, there are three conditions basically. There are three conditions. The very first condition is all carbon should convert into CO2. No CO should be formed. No CO should be formed, right? Correct? Okay, no problem. Then another one is all hydrogen should convert into H2O. Fine. And there should be, acha, one more thing, one more person can do, another person do what? They may do that, okay, sir, put here more oxygen, sir, more air supply, sir. Here, 2 times of this required, you supply 3 times, sir. What is the problem? Combustion will be complete only, but that is not perfect combustion. Why? Because if you are supplying extra air, that extra air will also take some amount of energy and go out as a air only. Let's say 2 kg air is required for combustion. You are supplying 3 kg. So 1 kg extra will do what? It will just take, it will enter at 30 degrees centigrade and go out at 1000 degree temperature. So basically it will carry the heat and waste the heat, right? So perfect combustion means there should no any extra oxygen remaining here. All the oxygen should be utilized. Nitrogen we can't do. Nitrogen is free of cost, right? So what we can say, there should no excess oxygen at combustion product. So this is called as what? Stoichiometric mixture, right? That if like stoichiometric mixture is sufficient amount of exactly sufficient amount of air is available. Exactly sufficient amount of air is available to burn all the fuel. If you want to burn, let's say, if you want to burn 1 mole of CH4, 1 mole of CH4 completely, perfectly, right? Then 2 kilomole of 2 mole, sorry, this is 1 mole, na? So 2 mole of oxygen is or 2 mole of air is required. 2 mole of air is required. Mass basis it will be different. Mass basis it will be different. So I hope you are able to understand this part. So that is called as stoichiometric. Stoichiometric means exactly how much amount is required. Correct. We will calculate also. Don't worry. We will calculate. Don't worry about it. Right. Don't worry. We will calculate this. First, you just write it down. First, you just write it down. First, you just write it down. So let's say 1 mole of CH4 is there. 2 mole of air is there, and this will form. Have you done this? Okay. Let's move, and now I'm going. This equation is written in form of moles. In form of moles. Now I'm going to convert this moles into mass. Now I'm going to convert this mole into mass. Right. So again I'm going to write this equation in next slide. Right. So let's say this is a CH4. I will write with the same color. So CH4 plus 2 times of O2 plus 79 by 21 times of N2, that equals to CO2, 1 CO2 plus 2 H2O plus what is remaining? That's it, I think. 2 times of CO2, or nitrogen will be there also. So 2 into 79 times of 21 and 2 plus heat will be there. Plus heat will be there. Plus heat will be there. Clear? Now everyone look at here. So just assume that here 1 mole of, this is air. This is basically our air. Packets of air, na? This is 1 packet of air. This is air. 1 packet, so basically 2 packets of air is required, right? Then so 1 mole of CH4 is going to combine with 2 moles of oxygen, then it will give 1 mole of CO2, 2 mole of H2O, and this much mole of nitrogen. But mass, how we will convert? Very simple, bhaiya. Moles are given. How to convert into, this is a stoichiometric equation. So one more thing I will tell you. This is a stoichiometric equation. Stoichiometric reaction. Stoichiometric reaction. Stoichiometric reaction means sufficient amount of air is present. Sufficient amount of air is present. Okay. Now let's talk about the mass. So here how much mass will be there? here tell me how much mass will be there. So mass is equal to, you already know bhai, mass is equal to what? Here I am writing mass is equal to number of moles into molecular weight, right? So just write here. So number of moles is here 1 into molecular weight is how much? Molecular weight is this carbon is 12, hydrogen is 1144, okay, gram. This will come in gram. Then this I will write. Actually I know about this, but okay, I'll write. So here number of moles are 2 into oxygen is 32 plus 79 by 21 times of 28. Okay, 28. Okay, so here 1 mole of, so 1 into carbon 12 plus O2 is 16 to the 32. Then this value is 2 into, all are in gram, 2 into hydrogen is 2 plus 16. Then this one I can write 2 into 79 by 21 times of 28. Right, let's calculate the mass, right? So this value will become like the total weight, total molecular weight of fuel is how much? 16. Air is how much? Mass of the air, this is 16 gram. So for 16 gram of CH4, for 16 gram of CH4, how much gram of air is required? How much gram of air is required? 79 by 21 into 28 plus 32 into 2. This is 274.667, for example. Right? Okay. So to burn 16 gram of CH4, if you want to burn it completely, then 274.667 gram of air will be required, which will produce 32 plus 12, 44 grams of CO2, and 16 plus 2, how much? 16 plus 2, 18 into 2, 36 gram of H2O, and 79 into 21, sorry, 79 by 21 into 28 into 2, and 210 gram, 210.667 gram of N2. Now do one thing. Left hand side you just sum. Before reaction, how much mass was there? Before chemical reaction, how much mass was there? So 274.667 plus 16, so it is 290.667 gram. And after reaction, how much mass is there? 44 plus 36 plus 210.667, you will get exactly same 290.667, not even fraction of change. This is law of conservation of mass. This is law of conservation. Number of moles are changing. The number of moles are little bit here and there might be possible, but if you see, right, because the moles are combining with other particles, right? Like one is participating other, another is participating other. So basically the total mass of like left hand side is equal to total mass of right hand side. So until unless Einstein is not came into the picture, right? Einstein, sir, E equal to mc square, mass can convert into energy. That is separate scenario at all. That is something different, right? Plasma state and that atomic reaction, like atomic bomb and all other. That is another thing. That is not the part of your discussion. So in your discussion, law of conservation of mass is valid. Law of conservation of mass is valid. So this time, whatever before the combustion, whatever mass is there, after combustion also same mass will be there. Only the energy which is associated with bonds, so bond will interchange and lot of energy will release. Don't think that mass is converting into heat here. Don't think that mass is converting into heat. No, mass is not converting. Only bonds are interchanging. That's it. Bonds structure is going to be changed, and then this much amount of heat is going to be produced. Now you see, when mass will convert into energy, huge amount of energy will come. Huge. Correct? So that is different scenario. So we are not talking about that particular scenario. Okay. Now if I talk about what is the air fuel ratio. Now I am going to talk about air fuel ratio. Air fuel ratio. Now air fuel ratio is defined as mass of air to the mass of fuel, right? To burn a certain amount of fuel, how much amount of air is required? That is called as air fuel ratio. So in this case, what is air fuel ratio, right? What is the air fuel ratio? So mass of air is how much required? 274.667 divided by 16. So you will get 274.667 divided by 16. So how much required? 17.166, something like that, right? So this is a stoichiometric air fuel ratio. This is called as a, because this equation is stoichiometric reaction, right? Two more are there, I will tell you. So this is called as stoichiometric air fuel ratio. Similarly, one more term is there, that is called a fuel air ratio. Fuel air ratio, same, opposite of this. Mass of fuel by mass of air. This value will get a 16 by 274. So 16 by 274.667, that is equals to, this value will come 0.05825. Okay, this is also called as stoichiometric fuel air ratio. Stoichiometric fuel air ratio. You just write it down first. You just write it down. Done? Okay, right. Perfect. So below this, write this statement also. This statement also you write. Please write this particular statement. The stoichiometric air fuel ratio is the ideal ratio of air. Stoichiometric air fuel ratio is the ideal ratio of air fuel that allows for complete combustion of fuel. Complete combustion of fuel with no excess oxygen or fuel remaining. Correct? So this part, no excess oxygen and fuel remaining, and it is a complete combustion. Complete combustion means, you already know, complete combustion means all carbon will convert into CO2, all hydrogen will convert into H2O. So in this line you write, right? Example again, gasoline, right? If you take the example of gasoline means petrol, right? If you take the example of petrol, like we have seen that na, for CH4 air, like stoichiometric air fuel ratio is 17.166, right? It means that for 1 kg of methane, for 1 kg of CH4, 17.166 or 17.2, you can say 17.2 kg of minimum air is required. If you supply less than that, then some of the carbon will not convert into CO2, then it will become CO, it will may form CO. Okay, write down this one. So similarly for petrol, actually it is a 14.7:1, 14.7:1, right? 14.7:1 actually. So for combustion of 1 kg of, even you can remember 15, no problem. 14.7 is exact one, but roughly in most of the book you will find 15. You will find 15, right? So it means that to burn 1 kg of petrol, 1 kg of petrol, how much amount of air is required? 15, nearly 15 kg of air is required. 15 kg air is required. Here one more exercise we'll do, and then we'll move on to the rich mixture and lean mixture, right? One more thing I'll do, the percentage of mass percentage of combustion products, mass percentage of combustion products, right? So here I'm going to write the mole. First, should I write mole percentage? Okay, mole percentage of combustion products, right? So first of all, total number of moles, total number of moles, how much total number of moles are there? You can see 1 mole of CO2 is there, 1 mole of CO2 is there, 2 mole of H2O is there, and 2 into this much mole of N2 is there. So CO, like 1 mole of CO2 plus 2 mole of H2O, 1 mole of CO2 plus 2 mole of H2O plus this value will come 3 point something, right? So 79 by 21, there is 3 point something, it will be 3.76 into 2 I will do, right? That will be a 7.52381 mole of N2, right? So total how much it will come? So total it will come this much plus 2 plus 1. So this value will come 10.52381 mole of combustion products. Let's say percentage mole of CO2 is equal to 1 by 10.52381, that is equals to how much percentage? This value will come 0. into 100 I will do. This value will come 9.5%. So in the combustion product, 9.5% oxygen CO2 will be there molar basis. Percentage mole of H2O is equal to, it will be 2 times, है ना, 2 by 10.52381 is equal to 2 by 10.52381. %. Remaining is N2. So 19 plus 9.5, 100 minus answer 71 percentage mole of nitrogen. Directly I am writing 71.5%. Now I am going to talk about mass of mass percentage of combustion products. Right, mass percentage of combustion products. Please listen here carefully. So mass percentage of combustion products will come how much? Okay, so total mass of combustion products is equal to okay, mass wise, let's see, 44 gram CO2 is there. The total already we have calculated na, 290.667 gram. 290.66 gram. We have already 290.66 gram. Okay. Now percentage mass of CO2. This value will come how much? 44 by 290.667. That is equals to 4 by 290.667. So this value will come 15.137%. Okay. Percentage mass of H2O. H2O was how much? 36 by 290.66. See, mole wise water was more, but mass wise water will be less because water is light compared to CO2. Correct? Water was light. Okay. So so this value will come 12.385%. Percentage mass of N2 to 10.667. 10.667. So 72.24%. So this is also sometime they are asking. Okay, please write it down. So we know that how to calculate stoichiometric air fuel ratio. Stoichiometric air fuel ratio. Now I think you already know how to calculate stoichiometric air fuel ratio. Okay, one thing, like leave some place in rough copy, rough page or just next page. Just next page, you one exercise I want to do so that you will be comfortable with this, then only we'll go for further, right? So I will also leave some space here, right? I will also leave some space here and then I will come. So now one small question I am writing for you, it which find the air fuel ratio of find the air fuel ratio stoichiometric air fuel ratio. Find the stoichiometric air fuel ratio of propane. Propane is fine. Propane you already know, C3H8. I can write here C3H8. Everyone please try to solve this, right? Everyone please try to solve this. Everyone please try to solve this. So okay, let's continue. So most of the students are giving answer like 15.67, but we will cross check once, right? So basically we have propane, that is C3, like C3H8, right? And with the help of air means what? Air means O2 plus 79 by 21 times of N2. That is we want stoichiometric air fuel ratio. So in stoichiometric equation, what will happen? First, all the hydrogen will convert into uh, H2O. So it will be 8H2O. 8H2O. No, 4H2O. Sorry, 4 total 8 is there, na? So 4H2O. Fine. Then whatever carbons are there, that carbon will form CO2. So plus 3CO2. Now we'll balance the oxygen. So how many oxygens are here? There 4 and 6. 4 and 6 means 10. 10 means here it will come 5. So here you will get a plus 5 into 79 by 21 times of N2 plus heat. Okay, so we have to find out air fuel ratio, right? Air fuel ratio. So I'm doing little bit fast. So what is the mass of this element, right? Mass of this, let's say this is 1 mole of C3H8. 1 mole of C3H8 will be 1 into 1 mole of C3H8 is equal to C3, or shall I directly write? Directly I will write. We have to find out air fuel ratio, right? Air fuel ratio in stoichiometric condition. So I can write here the mass of air divided by mass of C3H8, correct? So mass of air is what? Number of moles of air is known, right? Number of moles of the air is known. Mass is moles into molecular weight. So mole into molecular weight is, this is 32 plus 79 by 21 times of 28 divided, this is mass of the air, and then mass of C3H8, 1 into C3, so 3 into 12 plus 8 into 1, right? So just calculate, so it will come 79 by 21, sorry, 79 divided by 21 into 28 plus 32 into 5. So this value will come 686.667 divided by this one, 12 into 3 plus 8, this is 23, that is equals to 686.667 divided by 23. So this value will come 29.85. No, this is a mistake, sorry, here I did mistake. 12 into 3 is there, okay, plus 8, 44 will come here. Right, so 686.667 divided by 44, this will come 15.6. This is the air fuel ratio of stoichiometric mixture, right? Now write heading rich mixture, right? Now write heading rich mixture. So stoichiometric mixture you have already seen. Now I'm talking about rich mixture. This part is also done. Rich mixture. What is rich mixture? Who is rich? The people who have more fuel, obviously, right? If you have more fuel means you are rich, right? Because air is free of cost, fuel is costly, so more fuel means rich mixture, right? So a rich mixture has less amount of air. A rich mixture have less amount of air, and more fuel, is there compared to stoichiometric ratio, right? Let's say air fuel ratio, if I talk about just previous case, if I see this case, let's say this case only, let's say C3H8 propane I'm talking about. So to burn 1 kg of propane, 15.6 kg of air is required. 15.6 kg of air is required. But if you have less amount of air compared to stoichiometric, means let's say you have only 12 kg of air available. 12 kg air available to burn 1 kg of propane. In that case, what will happen? Incomplete combustion will be there. Some of the carbon will not able to convert. Into CO2. Why? Because of less oxygen. So this is called as what? Incomplete combustion. That is called as incomplete combustion. Correct? Incomplete combustion. And obviously when complete fuel is not burning, right? So there might be chances some of the fuel will left over, right? There might be chances that CO will form. There might be chances that some carbon particle will be remaining, right? So these things will be producing. So as it is an incomplete combustion and the fuel is not burning completely, so obviously less amount of heat will produce, so engine will produce less amount of power also. So which leads okay, which lead more power, more power. What is the reason I'm telling you? More power means if you are comparing with stoichiometric, then actually more power will come. Just wait for some time, you will get to know this, right? And more emission will be there, right? More emission will be there and lower fuel efficiency will be there. See, efficiency will be efficiency will be lower, but in rich mixture actually power is going to be more little bit. I'll give you one example, right? I'll give you one example. Let's say when you are throttling your wall complete, like accelerator when you are taking na, when you are taking accelerator completely, in that scenario, if you see, so your bike will move very fast. Your bike is going to be move very fast. Very fast it will move. Correct na? At that time, whatever mixture we are supplying, that is actually a rich mixture, means more fuel is there. Sir, when more fuel we are supplying and combustion is not complete, then how more power will produce? Because if complete fuel will not burn, so obviously that much amount of heat will not release. You are correct, but the point is, when less, like let's say, if complete fuel will burn, then total 1 megajoule heat is produced, for example. But the amount of air is more inside the cylinder, yes, right? For complete combustion, the amount of nitrogen is more, yes. So out of 1 megajoule, let's say 0.5 megajoule is taken out by the air itself. 0.5 is taken out from the air itself in outside. That is one problem. Whereas maybe there are some particles, some little bit incomplete combustion is there. So let's say only 0.8 megajoule heat is produced. Fine, but the amount of air inlet is also less. The amount of nitrogen is also less. Majority part of heat is taken out from by the nitrogen itself. So now even though less amount of heat is produced, but the energy taken out by that air is comparatively low. Now it is, let's say, 0.3 only. Now let's say it is 0.3 only. So in that case, 0.3, if it is gone under 0.5 will produce, right? Power will may produce. Even 0.2 maybe go out. So 0.6 may produce, correct now? So that's what, if rich mixture is there, so mostly we have seen that, right? Mostly, not in always, right? In some cases, if very rich mixture is there na, so power produce will also be very less. Even sometime engine may not start also, right? That possibility will also be there. But mostly we are seeing that the power is more, but emissions are also more. In emissions you will get CO, right? You may get carbon particles, you may get other harmful things, right? So government will not allow you, right? Too much rich mixture, they will not allow you, correct? And the lower fuel efficiency, obviously complete fuel is not burning, so the amount of heat produced, if you see, that is lower only, correct? Okay, now another one is, next heading you write lean mixture. Next one you write lean mixture. So whenever we are providing lean mixture means less amount of fuel, and more amount of air, less amount of fuel and more amount of air than stoichiometric. Actually, sir, why not only stoichiometric, bhai? Say, just let's say you have this propane as a fuel, correct? Propane as a fuel. Stoichiometric ratio is how much? Okay, not this one, this one. So stoichiometric mixture is how much? 15.6. Stoichiometric mixture is how much? 15.6. So it's better to put 15.6. What is the problem on that? The problem is that mixture is not uniform. The mixture is never uniform. So there might be possibility that in some places only fuel is there. In some places air concentration is more. So even though sufficient amount of air is present, then also incomplete combustion will be there. There is possibility. There is a possibility. So if you want to ensure that, all fuel will burn, there should be no any CO. In that case, it's better to supply little bit more amount of air, little bit more amount of air you supply, that will be always better. But because of that, power will reduce, right? More combustion, the lower emission, right? But potentially less power outcome will be there because more air is there, so more energy it will take it out, right? More energy it will take it out. But okay, no problem. But combustion will be complete, emission will not be there, any CO will not form, and it is fine, right? So actually we always put little bit our whenever we are cruising mode, you understand there are different modes during whenever we drive a vehicle. So at the time of starting, rich mixture is required, because if mixture will not be rich, then there might be possibility that nearby spark plug only air is there. So even though spark is happening but fuel is not burning, correct? Or that engine is also cold only. So cold starting also rich mixture is required. After that, whenever we are taking accelerator, then more amount of fuel is added actually to get more power. So at that time also rich mixture is there. When it is cruising, let's say you are cruising at 60 kilometer per hour, correct? With your bike 60 kilometer per hour, you are cruising. At that time, little bit lean mixture is there. And you will get good economy, decent power, right? And everything, low emissions, no problem at all, and maintenance will also be very fine. So always try to run your engine, right, run your bike at the range of 60 to 70 kilometer per hour only. If you drive less, then also it will consume more fuel, correct? If you drive very high speed, zoom, then also it will consume more fuel, correct na? So that's why my suggestion is to always, and it is safety guideline also, like safety wise also it is very good. Health of bike will be also very good, because whenever you are taking too much energy, so there are some, because then rich mixture will be there. There might be possible that nearby cylinder, some region, very high rich mixture is there, which will burn instantaneously, and it will damage the part, it will damage, some cavities may form, right? And these cavities will slowly explode, and the shape of the cylinder itself will change, correct? So you need to go for reboring and all, then engine will be waste, then performance will be go in dabba, right? Performance will go in dustbin, correct? So if you want to maintain the performance of engine, always drive in economy mode and cruising mode. Always try to, even though if you are in city, it is not possible to drive always in cruising mode, but always try to be in cruising mode, slow mode. And see, low speed you cannot avoid, because if it is required you have to go with low speed. Low speed means very low speed, because traffic is there and all. But high speed you can avoid, right? Right, if you think that you want to go to meet your girlfriend, it will take half an hour, take 15 minutes extra. What is the problem on that? Okay, so these are the definition of rich mixture and lean mixture, correct? Now with the same example which I have given earlier, right, this example, stoichiometric air fuel mixture I have already done. Now I am going to do with the lean and rich mixture also, right? Lean and rich mixture, right? Okay, so this equation again I am going to use this particular equation. So here I'll write, okay, combustion of CH. Actually, I am taking example of CH4, but anything you can take, it will be exactly similar way. There is no any difference at all. There is no any difference at all. So let's say, what is the equation actually CH4? CH4 equation is what? How many? Okay, 2 times. Okay, CH4. So equation I'm writing CH4 plus 2 times O2 plus 79 by 21 times of N2 is equal to CO2 plus 2H2O plus CO2 plus 2H2O plus 2 into 79 by 21 times of N2. Now plus heat will be there obviously. Now please listen here carefully. Now let's say it is given that it is a stoichiometric reaction. And air fuel ratio is how much? Or fuel air ratio, like air fuel ratio is how much? Air fuel ratio 17.166. This is 17.166. Fuel air ratio 0.058. How much? 25. Right, this is the stoichiometric that you have already studied. Now come to the case 1. 25% less air is available. Is rich mixture. Right? Let's say you have rich mixture, my dear student friends. Right, my dear student friends, you have a rich mixture. 25% of less air is available. In this particular case, right? In this particular case, what is the value of, what is the air fuel ratio that you have to calculate? Air fuel ratio, okay, with that we can calculate, but complete reaction we should write. We are interested to write a complete reaction. Okay, first we are interested to write complete reaction. Okay, so CH4, no problem. CH4 will be there, 1 mole of CH4. So to burn 1 mole of CH4, how many mole of air is required? 2, right? 2 mole of air is required. 2 mole of air is required. It is fine. Yes, sir. But actually 25% less is available. Means available is how much? Only 1.5 times, 1.5 moles, right? So basically minimum requirement is 2.5, 2 actually, but available is 1.5. 1.5 O2 plus 79 by 21 times of N2. Right. Now you have to write the equation for this. So now you have to follow the rule. Now you have to follow the rule. Sir, what is the rule? The rule is first all the hydrogen will convert into H2O. All the possible hydrogen will convert to H2O. So 4 hydrogens are there, H2O, so 2H2O. 2H2O, right? Achha, how many oxygen we have? 3 oxygen we have. Please listen here, right? 2 into 1.5, how much? No. 2 into 1.5, 3, right? 2 into 1, total 3 oxygen we have, right? 3 oxygen we have. Out of this 3 oxygen, out of this 3 oxygen, 1 point, sorry, out of this 3 oxygen, 2 oxygen is taken by hydrogen. Remaining how much oxygen? Only 1 oxygen is remaining. So only one carbon will get, only carbon required how much oxygen? 2 oxygen required to make CO2, but he will not able to make CO2. So what will happen? Plus CO will form, right? Dangerous. CO is basically dangerous for us, but still it is forming. Means you can see that in your combustion chamber, if less amount of fuel you will supply, less amount of air you will supply, then CO will form. Sometimes they are asking that why CO is forming, because of less amount of oxygen we are supplying, right? Okay, plus what is remaining? Oxygen over, right? So finally we are getting 1.5 into 79.21 times of 21 times of this equation we will get. This equation we will get. This equation will get, right? So, and if I calculate air fuel mixture here, air fuel mixture for 25% rich mixture, if you see, then this value will become mass of air. Mass of air is how much? 1.5 into 32 plus 79 by 21 times of 28 divided by 1 into 12 plus 4. Just calculate this. Fuel air ratio also calculate. 25%. Rich लिखना जरूरी है. Rich. How much you will get? 12.871. 79 by 21, 28. This value will come 12.875, right? 12.875. Fuel air ratio will get 1 by this one, 0.077. Okay, now there is another term I would like to introduce here. I would like to introduce here one more term, that is called as equivalence ratio. That is called as equivalence ratio phi. There is one term that is also called as equivalence ratio. The equivalence ratio is a measure of how rich or lean air fuel mixture is there, or fuel air mixture is there. So it is defined like phi, right? It is defined as the fuel air ratio of actual fuel air ratio to the fuel air ratio of stoichiometric. So if phi value is 1, what does it means? What does it mean? It means that actual fuel air ratio and stoichiometric air fuel ratio is same. So actually it means that stoichiometric air fuel air ratio, stoichiometric mixture. Now if the phi value is greater than 1, it means that phi value is greater than 1. Greater than 1 means what? If it is more than 1, it means that actual fuel air ratio is more than 1, right? Actual fuel air ratio is more than stoichiometric, means more fuel is there. More fuel is there means rich mixture. So this means that it is a rich mixture. And if phi is less than 1, it means that it is a lean mixture. So if suppose this is a, we just write it down. So in any case, we can calculate the equivalence ratio also. In any case, suppose in this case, if you see that, suppose in actual we are supplying 25% less amount of air in CH4. So fuel air ratio will be different. So what is the equivalence ratio? So you need to calculate equivalence ratio, and as it is a rich mixture, so equivalence ratio must come greater than 1. It must come greater than 1. So let's check once. Let's check here. So okay, so calculate phi value. Phi in this scenario, phi. So phi value will come fuel air ratio. Always remember it is a fuel air ratio, not air fuel ratio, right? Fuel air ratio of 25% rich, that is to the fuel air ratio of stoichiometric. This value is 0.07767 divided by 0.05825. This value will come how much? Calculate. 0.7767 0.07767 divided by this value will come 1.33. So equivalence ratio is coming 1.33, correct? Equivalence ratio is coming 1.33. One more case we'll take for lean mixture also. So let's take another case, that is case 2. %, this time I'm taking 50% more air, means lean mixture. So now how the actual equation will come? So basically we have CH4 plus oxygen is like air is there, oxygen plus 79/21 times of N2, that is equals to. So for 1 mole of CH4, minimum 2 moles of air is required. 2 moles of air is required, correct? Ideally stoichiometrically. Now 50% more is available. So 2 is not available, 3 is available. So basically here 3 is available. So now what will happen? Now how the equation will come out, right? So for this it is very easy. What we will do? So first all the hydrogen will convert, even though here more than sufficient air is there, so no problem. So here all the hydrogen will convert into oxygen, so 2H2O, correct? Then all the hydrogen will, sorry, CO2 will also form properly, plus. Now you need to check how much oxygen is still remaining. See here, how much consumed? 2, 4, 4 consumed. But actually we have 6. So 1 O2 is remaining. 1 O2 is extra. 1 O2 extra. So it will simply go into the atmosphere, right? Plus 3 into 79 by 21 times of N2. Okay, this equation will come. Percentage also you can write, right? Okay. Now come to the point like air fuel ratio. So if I want to calculate air fuel ratio for 50% lean, so how much you will get? Mass of air is 3 into 32 plus 79 by 21 times of 28 divided by 1 into 12 plus 4. If you solve this, 79 by 21 into 28 plus 32 into 3 divided by 16. This value will come 25. Wow, 25.75%, right? And fuel air ratio will come 50% lean, 0.033835, right? If I calculate phi value, so this value will come actual 0.038835 divided by 0.05 0.05825. So this value will come 0.66. Correct? Is it correct? So this is all about this particular chapter. So this particular chapter is very simple. You need to know what is combustion, what is thermochemistry. Then you need to know what is a fuel structure, how a hydrocarbon actually burns, what is a stoichiometric mixture, what is a lean mixture, rich mixture, how to calculate air fuel ratio or fuel air ratio in different cases, and how to find out the equivalence ratio, right? So this is all about topic. On this particular topic, if you go and check your PYQs, then approximately you will find 8 to 9 questions in last 10 to 12 to 13 years. In last 12 to 13 years, you will find approximately 7 to 8 questions. Means mostly every two years once a question is asked from this one. Very simple questions are there. Each and every question you will able to solve, no problem, right? So now it's time to solve few more problems for practice, right? Equivalence ratio is also done. So now this is a question. This is the question. Propane already I told you, C3H8. C3H8, the burned completely in the presence of air, complete combustion is there. So sir, propane I already told you. What is the equation? C3H8 plus, right, O2 plus 79 times of 79 by 21 times of N2, 70 and N2 is equal to complete combustion is there. So 3 CO2 will be there plus 4 H2O will be there. 4 H2O will be there, and propane we have already seen, so I'll do a little bit cheating, right? So 5 times. I'll do a little bit cheating here, so it will come 5. So plus 5 into 79 by 21 times of N2. Now, correct? So propane is burned completely in presence of air. Find the percentage of constituents in the product when the air has 21% nitrogen by volume. So volume basis means molar basis, right? Whatever percentage you have to calculate, that is molar basis, right? So total number of moles here, how much total number of moles will solve. If mass is there, then we have to calculate mass. We have already seen. So here 3 mole of CO2 plus 4 mole of H2O plus 5 moles of 5 into 79 by 21 moles of N2. So total how much? Total how much? Total is 5 into 79 by 21. This value will go 18.8. 18.81. 18.81 plus 4 plus 3. This value will come 25.81. Okay. So let's say percentage of CO2, if you calculate, percentage of CO2 will come 3 by 25.81. 3 by 0.116, right? Or 11.6%. One decimal limit I'm writing. Percentage of H2O value will come 4 by 25.81 equal to 4 by 25.81, 4 by 25.81. So this value will come 15.5%. Yeah, percentage of N2 remaining. $72.9. This is very simple question. Only you solve the problem which I am giving here. Most, even few questions are from previous year aerospace questions, right? And solve the DPP, you will able to solve all the questions. Even DPP is not prepared yet, so mostly you will get DPP on Monday only. Like after complete 2 DPPs are remaining. Have one more thing, one more information. 2 DPPs are will be a little bit late you will get, because I did not find because Saturday tomorrow also I am putting class, day after tomorrow also I am putting class, even some more work is there. So the DPP of thermochemistry chapter and DPP of the Breton cycle, maybe you will get little bit late, Monday Tuesday you will get, but I'll give you enough number of problems, don't worry. Here methane is there, CH4, presence of 10% of less air, right? 10% of less air. So basically methane is CH4, no? CH4 plus how much methane is 2 times, no? Methane equation we have already seen. Combustion of 2 times. So 2 times of, so actually 10% is less. So 2 का 10% means 2% less 2 into 0.9. 1.8. This value will come 1.8 na. So 1.8 times of O2. Then why 1.8? You understand na? Actually, to burn CH4 completely, how much amount of oxygen? How many moles of oxygen required? 2 moles of oxygen are required. But 10% less air is available, means 1.8 only. So O2 plus 79 by 21 times of N2 is equal to, now what I will get? So in this equation I have already told what you need to do, right? First convert all hydrogen to the this 2H2O directly, right? All hydrogen into oxygen. So okay, fine. So 2H2O. So 2 we have total 1.8 into 2. We have 3.6 oxygen, right? 3.6 oxygen, right? So this will happen. Then all the carbon will convert into plus CO. All the carbon will convert into the CO. All the carbon will convert into the CO, right? Right. So CO, how much remaining? 0.6 is remaining. How much? See, total 2 oxygen utilized, 1 more utilized, 3 utilized. Only 0.6 is remaining. So out of this one, 0.6 times of 0.6, see, one CO is there. Now second stage of carbon, like second stage of carbon will come. So 0.6 CO, 0.6 CO will convert into CO2 because 0.6 O is still remaining. So how much CO is still remaining? 0.4. 0.4 plus same 79. This point is very much clear, right? 0.4 CO. You just balance the equation, you will get the same. Don't worry. This is the way. 1.8 into 79 by 21 and 2. Please try to understand how to write the equation. First, hydrogen will burn. So for hydrogen, 2 oxygen are required. Already 3.6 is there. So 2 oxygen is taken by hydrogen. Remaining is 1.6. Then one oxygen will combine with C, make it CO. Now still 0.6 is remaining. So 0.6 CO will come out from here and form CO2. 0.6 CO will come out from here form CO2, and remaining CO is how much? 0.4 only. Now you just write how many moles are there total. The total number of moles basically 2 moles plus 0.4 moles plus 0.6 moles plus 1.8 1.8 into 79 by 21. This value will come 6.771 plus 0.6 plus 0.4 plus 2. So this will total, it will become 9.7714. Right. Now percentage of H2O, how much it will come? Percentage of H2O is 2 by this value. 2 by answer. So this value will come 20.46%. And percentage of CO 0.4 divided by 9.7714. So this value will come 4.09 3%. Percentage of CO2 0.6 divided by 9.7714 6.14%. Percentage of nitrogen 6.771. I hope you are clear with this. I hope you are clear with this. Anything else you required? Up to here is clear. Shall we move to the next problem? Shall we move to the next problem? Great. Let's move to the next problem. Now here, for the complete combustion of 1 mole of ethanol, ethanol is nothing but that's the thing which we drink mostly. In our whiskey and all, mostly ethanol is there. And even ethanol blend, that in petrol we are blending the ethanol, right? So the required number of moles of oxygen. So how many number of moles of oxygen is required, that we need to find out for complete combustion. For complete combustion, how many moles are required? So listen here, C2H5OH, okay, plus only we required oxygen, so no need to take air, because we want what? We want only number of moles of oxygen. So directly consider oxygen. What is the meaning, right? So O2 only consider. Even though if you write 79 by 21.92, that will not affect your answer. So I'm writing this. That is equals to, if you say, okay, I'll write 79 by 21 times of N2, okay. Even though they are asking only oxygen, it means they have only oxygen here. Even if you write, then number of moles of oxygen, air will come, and same number of oxygen will be there. So it's better to write O2 only, because they are asking oxygen. Complete combustion we required, okay. So complete combustion, what will happen? First you tell me what is the thing. Thing is, all the hydrogen will convert into H2O. So how many hydrogens are there? 5 hydrogen, 6 hydrogen. 6 hydrogen means 3 H2O they will form. 3 H2O they will form. Okay, very good. 3 H2O they will form, and 3 H2O gone. Then carbon dioxide plus 2 CO2 will be formed, right? Plus there should be no any excess oxygen. Now balance the oxygen. Here how many oxygens are there? 3 plus 4, 7 oxygens are there. But here we have one oxygen already, right? So how much required? See, this side 7, so this side also should be 7. So this one plus 3 oxygen. So I have 3 O2. 3 O2 is equal to total 7. Answer is going to be 3. 3 oxygen is required, or 3 O2 is required. So here answer will come 3. 3 O2 is required. Very good, very good, very good. Okay, next problem. A gas turbine combustor burning methane. Methane means CH4, and the air equivalence of 5 value is given. So actual phi value is given as 0.5, right? Means fuel air ratio of actual to the fuel air ratio of stoichiometric, correct? Definition also given, ratio of mass flow rate, uh, mass flow rate of the fuel to the mass flow rate of the air stoichiometric. If the air flow rate m dot of air value is given as how much? 20 kg per second, 20 kg per second. Then mass flow rate of methane, so m dot of CH4 they are asking how much. So I will do little bit short. See, we have already calculated fuel air ratio of CH4, so I am not going to calculate again, right? So fuel air ratio of in exam you have to calculate, fuel air ratio, of methane is how much? Fuel air ratio of methane is 0.05825, 0.05825, 0.05825. So this value is 0.0505825. So what is the fuel air ratio? Fuel air ratio, actual fuel air ratio is how much? Into 0.5, right? So 0.05825 into 0.5. Okay, so you will get a 0.029125, and that is equals to what? Mass of fuel, mass flow rate of methane. Fuel is methane na, divided by mass flow rate of air. So what is mass flow rate of methane? What is the mass flow rate of methane? 20. So here 0.029125 into 20. This value will come into 20. So this value becomes 0.5825 kg per second. So air flow rate will be 20 kg per second and methane flow rate will be 0.5825 kg per second. Clear है आदित्य नारायण? आदित्य नारायण, please check. Let's move to the next problem. A combustor is operating with a fuel air ratio of 0.03. Fuel air ratio, the fuel air ratio actual 0.03. A combustor operating with a fuel air ratio, the stoichiometric fuel air ratio of the fuel used. So fuel air ratio of stoichiometric is 0.06. So what is the equivalence ratio? It is very very small. Correct, easy. So phi is equal to fuel air ratio of actual to the fuel air ratio of stoichiometric. This value will come 0.03 divided by 0.06. That is equals to 0.03 divided by 0.06.5. 0.5. Correct. Now next problem. Next problem you solve. In the combustor gases octane, right, C8H8 is there and the air are burned in stoichiometric proportion. Okay, so it required the flow rate of air is 1 kg per second. What should be the corresponding flow of octane? Very simple problem. So here it is a stoichiometric, right? Stoichiometric proportion. So C8H8 H18 plus O2 plus 79 by 21 times of N2 is equal to first complete combustion is going to take place. All the carbon will convert into CO2 and all hydrogen will convert into H2O. Correct. Now how much oxygen required? 8 2 ja 16 or 8 2 ja 16 है ना, 8 plus 2 हाँ 16 plus 9 16 plus 9 25. So 25 by 2, yeah, 25 by 2, 25 by 2 will be required, right? So what should be the required flow rate? Okay, air fuel ratio will required, okay, or if you say fuel air ratio, okay, so fuel air ratio in stoichiometric condition, so fuel is how much? Fuel is 1 mole into how much? 8 into 12 plus 18 divided by 25 by 2 into 32 plus 79 by 21 times of 28, right? This value will come how much? 8 into 12 this is 114 divided by 79 by 21 to 28. 1716.667, that is equals to 0.066407, right? So fuel air ratio stoichiometric is equal to mass of fuel, mass flow rate of fuel, where the mass flow rate of air. The mass flow rate of air is given as a 1 kg per second. So from here mass flow rate of fuel value will come same, 0.06640 kg per second. So A is going to be your correct answer. A is going to be your correct answer. Okay, solve this problem. A surrogate liquid hydrocarbon fuel approximated as a C10 C10H12. C10H12 is being burned a land-based gas turbine combustor with a dry air 79% 21% RC by volume. How many moles of dry air is required for the stoichiometric combustion of surrogate fuel? Dry air at atmospheric temperature and pressure. Okay, so plus O2 plus 79 by 21 times of N2 is equal to first here complete combustion they are asking, right? I think so, right? How many mole of dry air require stoichiometric. Yes, stoichiometric means all carbon 10 CO2. All carbon will convert into CO2 and 6 H2O. Right? So how many oxygen utilized here? 10 to the 20, 20 plus 6, 26. 26 by 2. So 13. Here it will come 13. So 13 plus 13, 70, 13 into 79 by 21 times of N2. So basically how many moles of air required? This is the number of moles of air. This is basically number of moles of air. Of moles of air. So our correct answer is going to be 13. Correct answer is going to be 13. Okay. Correct answer is going to be 13. Okay. Solve this particular problem. Combustion between fuel octane. Octane means C8H18. The oxidizer occurs inside the combustor with the following stoichiometric equation is already given. This one, you see, stoichiometric equation is already given here. So here you can see all carbon is converted into CO2, all hydrogen converted into H2O, and nitrogen remaining, right? The atomic weight of carbon, hydrogen, everything is given, even though we know about it. The combustor take place with the fuel to air ratio. Fuel to air ratio 2.25. The equivalent ratio we have to find out. See, actual fuel to air ratio is given, right? Actual fuel to air ratio we already know. What is that? 0.028. Now what we have to find out? We have to find out fuel air ratio. This is actual, not air. This is actual stoichiometric. So stoichiometric we need to calculate. So stoichiometric means how much mass of fuel. Mass of fuel, how much? 2 moles of C8H18 is there, right? Mass of fuel. C8 means 8 into 12 plus 18. This is the mass of the fuel divided by the air. Air is 25, I think. Okay. Air is 25 into 32 plus 94 into 28. So this value will come how much? So 8 into 12 plus 18 into 2. So this value will come 228 divided by 25 into 32 plus 94 into 28. 3432. This value will come 0.0664. Now we have to write the phi value. Phi is what? Phi is fuel air ratio of actual to the fuel air ratio of stoichiometric. So fuel air ratio 0.028 divided by 0.0668, right? This value will come 0.422. 0.0422. So B is going to be your correct answer. Yes, Ankit, very good. See, there are very good chances that one question will come from this topic. There are very good chances that one question will come from this topic as far as aerospace is concerned. So I suggest you please solve all these problems. Okay, so all the problems are over, so this chapter is also over. These are the important points that you need to remember, even it is already you have written. So thank you very much. So this topic is already over. Let's meet tomorrow at 11 a.m. and we'll start with a new chapter, that is Brayton cycle, right? The Brayton cycle, gas turbine cycle, correct? So basics of the Brayton cycle we'll study, and the application of this Brayton cycle in ramjet engine or gas turbine engine and all that you will study in uh, another part of jet propulsion, correct? So basic part where the basic concepts of thermodynamics is required, that I will teach you here. Okay, so I hope this chapter you are able to understand. Anyone have any problem with this chapter? Right, this chapter I think you understand clearly. Okay, so let's meet tomorrow at 11 o'clock. Thank you very much.